Hydroboration oxidation is a type of hydration reaction. In other words, it adds a hydrogen and an OH group to an alkene. Unlike the hydration reactions that we've seen before, it is anti-Markovnikov, although like the ones that we've seen before, the intermediate, actually the transition state, is still the most stable one possible. The stereochemistry of this is thin, which we'll look at in a minute. So if you recall hydration from before, we used water and an acid to form the most stable carbocation possible, and then water would add to give us that oxonium ion, and then after deprotonation we get the alcohol at the most substituted position. In hydroboration oxidation, however, we get the OH at the less substituted position. There's two kind of big picture steps to this reaction. In the first, we get this hydroboration step where we use borane, BH3. It's usually complex to something like THF. In any case, it adds to the less stable position. We'll look at why that happens in a second. And we get this compound that we can actually isolate called an alkyl borane. And this can be used in a variety of different ways, but here we oxidize it to give the OH at the same position as the borane was. So the mechanism explains both the syn stereochemistry and also the anti-Markovnikov regiochemistry. And the thing to remember about the BH bond is that the boron is actually less electronegative than hydrogen is. Hydrogen is more electronegative, so it has a partial negative charge. It forms a bond to the more substituted carbon. This is going to have a little bit less electron density at it because this carbon doesn't need those pi electrons quite as much to stabilize it. It has surrounding carbon-hydrogen bonds which can stabilize it by hyperconjugation. So it's a little bit partially positive. The less substituted carbon is partially negative because it has less of the carbon around it to stabilize it. And so it will, the carbon down here will be the one that forms the carbon-boron bond, and at the same time the boron-hydrogen bond, the electrons there, form a bond to the more substituted position. And so we wind up with a transition state that's cyclic. Because it's cyclic, you can't have a hydrogen on one side and a boron on the other. There's just not enough space in the cycle to do that. The bonds aren't long enough. So they're both going to add to the same side of the ring, which results in syn stereochemistry, syn addition, which you see here. And then oxidation, we replace the BH2 with the OH. Interestingly, it's not like an SN2 reaction. It's a little bit more complicated than that. You don't need to know the mechanism for it. And simply the boron is replaced by the OH, so it has the same stereochemistry. It's retained. And you can see that both enantiomers can form in one. The borane comes in from the top, giving this product, and in the other it comes in from the bottom, giving the other enantiomer.